On October 20th, 2025, the internet shattered. Amazon, Snapchat, Fortnite banks' entire networks flickered out, plunging the world into silence. All of it happened in a matter of minutes. And amidst this eerie stillness, a mysterious visitor from another star silently slipped behind the sun. 3I Atlas, the third interstellar object ever discovered, vanished from every telescope on Earth at the exact moment our digital world collapsed. Authorities called it a coincidence, a technical glitch. But in a universe governed by perfect timing, how many coincidences does it take before you start questioning if it's all part of some greater design? Stick around until the end as we unravel the outage, the orbit, and the chilling possibility that something out there might be the true cause of it all. If you're as intrigued by these mysteries as I am, make sure to hit like and subscribe so you don't miss a single part of this unfolding story. Drop a comment to let me know where you're tuning in from, what time it is in your corner of the world, and tell me, do you think we're getting the full truth or just the version they want us to believe? Share this with a friend, a forum, or in your group chat, because that's how the signal spreads. Together we will chase the truth, one anomaly at a time. Part 1 Outage. On the morning of October 20th, 2020, something broke, and not just a few servers or a single app. What happened was a cascade of failures that rippled across the internet like a digital earthquake. Amazon went dark, Snapchat vanished, Fortnite players stared helplessly at error screens, Ring doorbells stopped recording, Venmo transactions froze mid-payment. For millions around the world, the internet simply stopped working. Initial reports pointed to a massive outage in Amazon Web Services, specifically the US East 1 region in Virginia. But this wasn't just any server farm having a bad day. US East 1 is one of the most critical hubs of global internet infrastructure, a digital backbone that supports countless services we use daily without even thinking about it. When it fails, the effects cascade across continents. AWS called it a technical failure. Elevated error rates in their DNS and DynamoDB systems. Nothing to see here. Move along. But here's where it gets interesting, almost impossibly interesting. While engineers scrambled to restore service and millions of users frantically refreshed their browsers, something else was happening out in space. 3I Atlas, the third confirmed interstellar visitor to our solar system, was entering solar conjunction. If you're unfamiliar with the term, let me explain. Solar conjunction occurs when the sun positions itself directly between Earth and the object we're trying to observe. For astronomers, it's like a cosmic curtain dropping over the stage, right? When the most important moment of the show is about to happen. No telescope on Earth can pierce the blinding sphere of the sun to see what's on the other side. In essence, 3I Atlas was about to become invisible, slipping behind the sun, just as it approached its closest point to the sun. Its moment of highest energy and potential activity. Now, I know what you're thinking. Coincidence, right? Things break all the time. Cloud infrastructure has hiccups. Interstellar objects pass through our solar system on their own schedules. These events probably have nothing to do with each other. That's likely true. But here's what makes this particular coincidence so unsettling. Previous interstellar visitors like Umamu and Comet Borisov were observable during their closest approach to the sun. We could track them, measure their behavior, analyze their composition, and document any changes. But 3I Atlas is different. Its orbital geometry means it will reach its point of maximum solar influence, its perihelion, while completely hidden from Earth's view. We're about to miss the most energetic, most dynamic phase of this object's journey through our solar system because the sun itself will block our line of sight. Let me lay this out clearly. On October 20th, one of Earth's most critical pieces of digital infrastructure experiences a massive unexplained failure. Less than 24 hours later, an object from outside our solar system traveling on a hyperbolic orbit from the direction of the galactic center enters a period of total invisibility from Earth. Two blind spots, one digital, one cosmic, open at nearly the same moment. Maybe it means nothing, or maybe someone or something was counting on us not being able to see what happens next. Before we dive deeper, let me give you some background on 3I Atlas. This object was discovered on July 1st, 2025, making it the third confirmed interstellar visitor after Umamu and Borisov. Its trajectory is hyperbolic, meaning it's not gravitationally bound to our sun. It came from somewhere else, somewhere between the stars, and it's just passing through. Where it came from exactly, we can only approximate. Its inbound direction points roughly toward the constellation Sagittarius, which also happens to be the direction of the galactic center, the supermassive black hole around which our entire galaxy rotates. Whether that matters, we'll explore that later. What matters now is that this object is real. It's here, and for the next week or so, we won't be able to see it at all. The speculation online started immediately. Forums and social media lit up with questions. Was the timing really just a coincidence? Could someone have used the cloud outage as cover for unusual activity? What happens when two of the most critical systems we depend on, our digital infrastructure and our cosmic observation network, both go dark at the same time? Most of these questions don't have clear answers yet, and that's exactly what makes them so compelling. We live in an age where we expect to know everything, to have eyes everywhere, monitoring every system, tracking every object. But on October 20th, we were suddenly blind in two directions at once. Here's why this matters beyond just the inconvenience of your favorite apps being down. For a few hours, global infrastructure has become increasingly vulnerable because it's so centralized. A handful of cloud providers now control the majority of internet services. When one region of one provider fails, the cascading effects can shut down everything from social media to financial systems to emergency services. We've built a digital civilization on a surprisingly fragile foundation. At the same time, our cosmic observation network, those telescopes, satellites, and radar dishes scanning the sky, has significant blind spots. Solar conjunction is one of them. We simply cannot observe anything behind the sun, no matter how advanced our technology becomes. It's a fundamental limitation of our position in space. So what happens when those two vulnerabilities align? What happens when technological fragility and observational blindness overlap? That's the question we're going to explore in this investigation. We'll trace the data, examine the patterns, and ask whether this outage was truly just a random technical failure, or something more deliberate, more coordinated. And we'll look at what 3i Atlas might be doing right now, while we can't see it, and what that could mean for our understanding of who or what is watching us from the darkness between the stars. Part 2. Infrastructure Under Fire. Let's dive into what actually happened on that fateful morning. The AWS outage didn't just flip a single switch and shut everything down at once. It unfolded like a cascade. One failure triggering another, systems toppling like dominoes in a carefully balanced network. The timeline starts around 3:11 a.m. Eastern Time, when the first elevated error rates began appearing in the US East 1 region. Within minutes, DNS services began to fail. For those not familiar with the tech side, DNS acts like the phone book of the internet. When you type a website address into your browser, DNS translates that human-readable name into the numerical address that computers actually use. When DNS fails, the internet doesn't technically stop existing, but you lose the ability to navigate it. Your computer can no longer find anything. DynamoDB followed next. This is a database service used by countless applications for storing and retrieving data at massive scale. Then came errors with load balancers, the systems that distribute incoming traffic across multiple servers to prevent any single machine from being overwhelmed. One by one, the critical components that make modern internet infrastructure work began failing. By the time most people on the East Coast woke up, major services were already offline. Snapchat couldn't load messages. Fortnite players couldn't connect to game servers. Ring cameras stopped uploading footage. Venmo transactions hung in limbo. Even Amazon's own retail site showed errors for many users. The disruption spread across time zones as people around the globe tried to access services and found them unreachable. Thousands of reports flooded monitoring sites like Down Detector. The pattern was clear. This wasn't a series of isolated issues with individual apps. This was a failure at the infrastructure level, deep within one of the internet's most critical junctions. US East 1 isn't important just because it's large, though it certainly is. It's critical because of where it sits in the global network's topology. Major content delivery networks, streaming services, financial platforms, communication tools, and countless smaller applications all route through this region. When it fails, the effects ripple outward, touching nearly every corner of the digital world. Think of it like a major airport hub going offline. Sure, planes can still technically fly without it, but the disruption to the entire network of connections is enormous. So how rare are outages of this magnitude? AWS has had failures before. In December 2020, a problem with their Kinesis data streaming service caused widespread disruption. In November 2021, network device issues in US East 1 triggered another wave of outages. In June 2023, power-related issues caused service degradation. But failures that knock out this many high-profile services simultaneously, failures that last for hours and affect users globally, are genuinely uncommon. Amazon has built its reputation and business model on reliability, redundancy, sophisticated monitoring, and rapid response teams. When something breaks through all those layers of protection, it suggests either an unusually severe technical problem or something more targeted. This is where the cybersecurity angle becomes important. Cloud infrastructure failures don't happen in a vacuum. They highlight vulnerabilities in how we've structured our digital civilization. Supply chain attacks where malicious code is inserted into legitimate software updates have become increasingly sophisticated. Configuration errors where a single mistyped command can cascade into a system-wide failure occur more often than providers like to admit. State-sponsored threat actors, intelligence agencies, and military cyber units from various countries actively probe cloud infrastructure for weaknesses. The centralization that makes cloud computing so efficient also makes it an incredibly attractive target. Compromise one region of one provider, and you potentially affect millions of users and thousands of businesses simultaneously. Could a targeted actor exploit a global blind spot? That's the question that keeps security researchers awake at night. Imagine you're planning a sophisticated operation, something you want to execute without being detected. You need a window of opportunity, a moment when the defenders aren't watching or can't respond effectively. In infrastructure terms, a cloud outage creates exactly that kind of window. Monitoring systems go offline. Security tools lose visibility. Incident response teams scramble to restore basic functionality rather than searching for subtle signs of intrusion. If you wanted to move data plant malware or alter systems without triggering alarms, the chaos of a major outage would be the perfect moment to act. Now add the cosmic element. While terrestrial monitoring systems are degraded or offline, an interstellar object enters solar conjunction, becoming unobservable to every telescope on Earth. Two blind spots, digital and cosmic, open simultaneously. If someone wanted to conduct operations in both domains without being seen, this would be the moment to do it. I want to be clear, this is speculation, not proven fact. There's no public evidence of coordination between the AWS outage and 3i Atlas's conjunction, but the pattern is striking enough that it demands attention. In astronomy, we call it a blind window, when an object passes behind the sun. In infrastructure security, we might call it a cloud-blind window. When monitoring and defensive systems fail, the terminology might differ, but the concept is the same. Invisibility creates opportunity. Cloud operations leaders have been warning about this kind of vulnerability for years. The industry has consolidated around a small number of massive providers. Amazon, Microsoft, and Google now control the majority of cloud infrastructure. When you concentrate that much of the internet's functionality in so few hands, you create single points of failure with enormous consequences. It's not that these companies are incompetent or careless. They employ some of the best engineers in the world and invest billions in security and reliability. But no system is perfect. The larger and more complex a system becomes, the more potential failure modes exist. Over-centralization makes the entire ecosystem fragile in ways that are difficult to fully anticipate. What if this outage was more than just a technical failure? What if the timing wasn't coincidental? These questions don't have clear answers yet, but they point to a larger truth about our moment in history. We've become profoundly dependent on systems we don't fully control and often don't fully understand. Most people have no idea what cloud computing actually means, or how much of their digital life depends on servers in specific buildings, in specific cities. We trust that the infrastructure will work, that when we open an app it will connect to distant machines and retrieve our data. When that trust is violated, when systems fail at scale, we're reminded of how vulnerable we've made ourselves. The digital world isn't solid ground. It's more like a web suspended in midair, strong enough under normal conditions but susceptible to catastrophic collapse if the right strand is cut. Part 3. 3i Atlas as Blind Passage. While engineers scrambled to restore cloud services 3i, Atlas continued its journey through the inner solar system following a trajectory that defies the patterns we're used to seeing. Most objects that visit our solar system are gravitationally bound to the Sun. Planets, asteroids, comets, they all follow elliptical orbits that keep them trapped in the Sun's influence, orbiting endlessly, or until some collision knocks them loose. 3i Atlas is different. Its orbit is hyperbolic, a term that means it's moving too fast to be captured. It came from interstellar space, the vast darkness between stars. And after its brief visit to our solar system, it will return to that darkness, continuing a journey that might span millions or even billions of years. While we know the basic parameters of its path, the details are still unfolding. The discovery happened on July 1, 2025, when automated sky surveys detected an object moving against the background stars with unusual velocity. Subsequent observations confirmed the hyperbolic trajectory and its interstellar origin. 3i Atlas is the third such object we've definitively identified, following Oumuamua in 2017 and Comet Borisov in 2019. Each of these visitors has taught us something new about the galaxy beyond our solar system, about the processes that fling objects into the void, and the characteristics they develop during their long journeys through space. 3i Atlas promises to continue that education, assuming we can observe it properly. Here are the critical dates. Solar conjunction occurred around October 21, 2025. That's when the object's position relative to Earth placed the Sun directly in our line of sight, making observation impossible with current technology. Perihelion, the closest approach to the Sun, happened on October 29, 2025, at approximately 1.36 astronomical units from our star. For reference, 1 astronomical unit is the distance between Earth and the Sun, about 93 million miles. While 3i Atlas won't get as close to the Sun as Earth does, it will come close enough to experience significant solar heating and radiation pressure. For a comet-like object, this is when activity typically intensifies. Ice vaporizes, dust streams away, and tails form and brighten. This is the most dynamic and scientifically interesting phase of a comet's passage, and yet we're going to miss it. That's the fundamental problem with this object's geometry. Previous interstellar visitors were observable during their perihelion passages. When Oumuamua reached its closest point to the Sun, telescopes around the world tracked it continuously, measuring changes in brightness, searching for outgassing or fragmentation, analyzing its unusual elongated shape. When Comet Boris made its approach, we documented its composition, its tail structure, and its carbon monoxide emissions. We gathered data that told us something about the star system it came from, and the conditions it experienced during its interstellar journey. With 3i Atlas, we get none of that. The geometry of its orbit means that during its most energetic phase, it's hidden behind the Sun. By the time it emerges from conjunction and becomes observable again, perihelion will be over. Whatever happened during those hidden days, whatever changes or activities occurred, we'll only see the aftermath. This is historically unusual. Interstellar objects are rare enough that we've only confirmed 3 of them ever. Each one is precious from a scientific standpoint, a messenger from beyond our solar system carrying information about conditions we can't directly observe. To have one of these rare visitors pass through its highest energy phase while unobservable is frustrating in the extreme. It's like having a once-in-a-lifetime opportunity to interview someone with crucial knowledge only to have them whisper their answers while a jet engine roars in the background. You know the information is there, but you can't access it. The trajectory itself has some interesting characteristics. 3i Atlas's orbit is inclined about 5 degrees relative to the ecliptic, the plane in which Earth and most other planets orbit the Sun. 5 degrees doesn't sound like much, but for an interstellar object, it's actually quite small. Most comets from the Oort cloud, the distant shell of icy bodies surrounding our solar system, arrive on much more steeply inclined orbits, sometimes nearly perpendicular to the planetary plane. An interstellar object with a relatively low inclination suggests either a particular origin point, aligned with our galactic disk, or possibly a trajectory that's been influenced by something other than random dynamics. Again, this could be perfectly natural, but it's worth noting. The scientific stakes are considerable. During the invisibility period, activity is likely to occur. Comets typically develop jets of gas and dust as solar heating vaporizes surface ice. These jets can be asymmetric, creating non-gravitational forces that change the object's trajectory in subtle but measurable ways. Fragmentation is also possible. If structural weaknesses exist in the object, thermal stress from solar heating can cause it to break apart. We've seen this happen with other comets splitting into multiple pieces that eventually disperse. With 3I Atlas hidden behind the Sun, we could miss the moment of fragmentation entirely, only discovering the event later, when multiple objects emerge from conjunction instead of one. There's also the possibility of more exotic activity. Some theories suggest interstellar objects might carry complex organic molecules, or even primitive life protected within their icy interiors. As solar heating penetrates the surface, these materials could be released and potentially detected through spectroscopy. But you have to be watching at the right moment to catch those signatures before they dissipate into space. Missing perihelion means missing that critical observation window. Whatever 3I Atlas releases during its closest approach to the Sun, whatever chemical or physical changes occur, we're likely to see only indirect evidence after the fact. So we have parallel blind windows again. Telescopes on Earth lose sight of an interstellar object precisely when it becomes most interesting. Digital infrastructure fails at nearly the same moment, cutting off services and communications globally. Two systems losing visibility simultaneously, one cosmic, one technological. The coincidence might mean nothing, or it might mean everything. What happens when no one is watching? What occurs in the gaps between our observations? These aren't just philosophical questions. They have practical implications for how we understand both the cosmos and our own technological civilization. Part 4. Anomalous Trajectories and Engineering Footprints. 3I Atlas hasn't been a typical interstellar visitor. Not that we have enough examples to confidently define what typical is, but from the earliest observations, this object has displayed characteristics that have left researchers scratching their heads. The spectroscopic analysis, which reveals an object's chemical composition by examining light reflected or emitted from it, showed unusual patterns. High concentrations of carbon dioxide, more than you'd expect from a typical comet, stood out. There was also significant nickel content, suggesting a composition more akin to an asteroid than an icy body, and surprisingly low water content, which is strange for an object that appears to be outgassing and exhibiting some comet-like behavior. Hubble Space Telescope observations added another layer of confusion. The object exhibited a forward glow brightness concentrated ahead of its direction of motion rather than trailing behind in a typical comet tail. Most comets develop tails that stream away from the Sun due to radiation pressure pushing gas and dust outward. But 3I Atlas's forward glow suggests a different mechanism at play, possibly linked to how material is being released from the surface, or how that material interacts with the solar wind. It's not something we've never seen before, but it's unusual enough to raise eyebrows. The lack of a classic tail structure only adds to the strangeness. You'd expect an icy body approaching the Sun to develop a visible tail, as volatiles vaporize and stream away. 3I Atlas, however, has been more subtle, more ambiguous in its activity. These oddities have prompted speculation, especially from researchers willing to entertain unconventional hypotheses. The pro-engineering view, though, I want to emphasize this, is not the mainstream scientific consensus suggests that if 3I Atlas were actually a probe, or technological artifact rather than a natural object, the timing of conjunction and perihelion would be perfect for maneuvers. This brings us to something called the Obath effect, a fundamental principle of orbital mechanics that applies to both natural comets and hypothetical spacecraft. The Obath effect works like this. When you're moving fast and you apply thrust, you gain more kinetic energy than if you applied the same thrust while moving slowly. This may seem counterintuitive at first, but it comes from how kinetic energy relates to velocity. Energy increases with the square of velocity, so changes in speed at high velocity translate into larger energy gains. For spacecraft, this means the most efficient place to perform a maneuver is at perihelion, when you're moving fastest relative to the Sun. A burn that changes your velocity by, say, 1 km/s at perihelion has a much larger effect on your total orbital energy than the same burn performed farther from the Sun, where you're moving more slowly. If 3I Atlas were a probe, and again this is speculative, perihelion would be the ideal time to perform a trajectory correction, deploy sub-probes, or change velocity to target a specific destination. The timing of solar conjunction means such maneuvers would be unobservable from Earth. You could alter your course, release payloads, or execute complex operations while the Sun blocks all terrestrial observation. By the time the object emerges from behind the Sun and becomes visible again, the maneuver would be complete, and the new trajectory would be established. There's a cybersecurity analogy here that's almost too perfect. In network defense, attackers often wait for maintenance windows or known periods of degraded monitoring to make their moves. If you know the defenders will be blind or distracted at a specific time, that's when you strike. The intrusion happens during the blind window. By the time monitoring systems come back online, you've already established your foothold, moved your data, or executed your payload. Post-incident forensics might eventually reveal what happened, but the crucial action occurred in the gap. Now I need to clarify the mainstream scientific view. Most astronomers and planetary scientists argue quite reasonably that natural cometary physics can explain 3I Atlas's oddities. Its unusual composition could reflect formation conditions in a different stellar system. Forward glows and asymmetric activity have been observed in other comets and attributed to specific outgassing patterns or surface properties. The lack of a prominent tail might simply mean the object has less volatile material than typical comets, or that its surface has been processed by cosmic rays during its interstellar journey. Every strange characteristic taken individually has plausible natural explanations. It's only when you stack them together and add the timing of conjunction that the pattern begins to seem less random. The directionality of the object also deserves attention. 3I Atlas arrived from the general direction of Sagittarius toward the galactic center. That's not unprecedented. Objects can come from any direction, but it does place this visitor along a corridor that we'll discuss more later. If interstellar space isn't entirely random, if there are preferential paths or gravitational structures that channel objects along certain routes, then an object arriving from the direction of the galactic core might be following one of those paths. Whether that path is purely natural or might be utilized by something artificial remains an open question. Tying this back to the infrastructure outage, we see a similar pattern. Hidden movement during a blind window plus system vulnerability equals opportunity for undetected action. In the cosmic case, an object with unusual properties enters solar conjunction at its moment of highest energy, potentially masking any maneuvers or releases. In the digital case, critical infrastructure fails at a moment when global attention is already divided, potentially masking data exfiltration or system compromise. The parallel is striking even if the connection is unproven. What would constitute evidence of artificiality? This is where scientists wisely urge caution. Claims of alien technology require extraordinary evidence. A trajectory change that can't be explained by outgassing or natural forces would be significant. Fragment releases that show geometric patterns or coordinated timing would be noteworthy. Post-conjunction analysis revealing manufactured materials or structures would be definitive. But absent such evidence, the scientific consensus leans toward natural explanations. Unusual, yes. Impossible, no. The pro-engineering view remains speculative, interesting for thought experiments, but not yet supported by hard data. Still, the timing and the geometry make this particular interstellar visitor a focus of more attention than it might otherwise receive. Part 5. The Spectacle and the Distraction. While 3I Atlas slipped into invisibility behind the Sun, and internet infrastructure burned through its crisis, something else was happening in Earth's sky. A show. A spectacle, the kind of celestial display that draws people outside to look up and marvel. Two bright comets graced the night sky in mid-October 2025, both visible to the naked eye under decent conditions, both generating excitement among amateur astronomers and casual skywatchers alike. Comet Lemon and Comet Swan, unrelated to each other and unrelated to 3I Atlas, were present in our sky at the same time, providing a visual feast while the interstellar visitor hid behind our star. Comet Lemon, officially designated C2I256, was discovered on January 3, 2025. Its inbound path brought it into the inner solar system on a trajectory that made it increasingly visible throughout the spring and summer. By October 20th, it had brightened to approximately magnitude 4, meaning under dark skies, away from city lights, you could see it without binoculars or telescopes. It appeared in the northwestern sky, after sunset, showing a greenish hue, characteristic of comets with significant carbon compounds. The greenish color comes from diatomic carbon molecules fluorescing in sunlight, a beautiful natural chemistry that gives some comets their distinctive appearance. Comet Swan, designated CTT25R2, was discovered more recently on September 11, 2025. Its trajectory placed it low in the southwestern sky during evening observations visible from southern latitudes and lower southern hemisphere locations. Not as bright as Lemon, but still accessible to patient observers with clear horizons. Two comets visible simultaneously is uncommon but not unprecedented. It happens occasionally when the random timing of cometary orbits brings multiple objects into the inner solar system at once. For anyone paying attention to the sky, October 2025 offered an unusual opportunity to observe multiple comets in a single night. Then there was the Orionid Meteor Shower, an annual event that peaks every year around October 20th through 22nd. The Orionids are debris from Comet Halley particles shed during that famous comet's previous passes through the inner solar system. As Earth's orbit carries us through this debris stream, particles slam into our atmosphere at high velocity, burning up in brief streaks of light we call meteors, or shooting stars. The peak night for the Orionids in 2025 fell right on October 20th into 21st, the same window when 3I Atlas entered conjunction and AWS experienced its outage. Observers with clear skies could expect to see 10 to 20 meteors per hour, at the peak bright streaks appearing to radiate from the constellation Orion. So picture the scene: visible comets in the northwest and southwest sky glowing green and leaving faint tails, meteors streaking across the sky every few minutes, remnants of the most famous comet in human history. A spectacular celestial display, the kind that gets people to put down their phones and actually look up for a few minutes. And behind the sun, hidden from all observation, an interstellar object reaches its closest approach to our star. While simultaneously thousands of miles below in Virginia, critical internet infrastructure fails, and millions of digital services go offline. The contrast is almost theatrical: the visible versus the hidden, the spectacle versus the silence. What we can see naturally draws our attention. Bright comets and meteors are immediately accessible, beautiful, worthy of photography and social media posts. What we can't see, an interstellar object behind the sun and the inner workings of cloud data centers, remains abstract, easy to ignore, until something goes wrong. There's a psychological principle at work here. Humans are wired to notice movement, light, and change. We're drawn to the visible and obvious, while the subtle and hidden often escapes our attention entirely. Magicians use this principle constantly, while they direct your attention to one hand or one part of the stage. The actual trick happens elsewhere in the blind spot created by your focused attention. Could the same principle apply on a cosmic or infrastructural scale? If someone wanted to do something unobserved, would you time it to coincide with a distraction? The visible spectacle of comets and meteors keeps casual observers looking up at the accessible sky, while the important action happens behind the solar curtain. The internet outage dominates headlines and user attention, while deeper activities could theoretically occur in the chaos and degraded monitoring. I'm not claiming this actually happened, but the pattern fits a recognizable template: distraction while critical systems go dark, spectacle while the real action unfolds in silence. Infrastructure systems work similarly. When major failures occur, attention and resources flow toward restoring basic functionality. Engineers focus on getting services back online, communicating with users, and managing the crisis. Less visible security monitoring might receive reduced attention during those critical hours. If you wanted to move through a network undetected, a period of major outage response would provide cover, not because defenders are incompetent, but because they're rationally prioritizing immediate problems over subtle anomalies that might only become apparent later. The meteor shower adds another layer. October 20th has been special for meteor observers for as long as humans have been watching the sky. The Orionids peak on this date every year like clockwork, a predictable celestial event. Anyone planning something and wanting to know when sky watchers would be looking up rather than monitoring other systems could simply check the astronomical calendar. Again, this might be reading patterns into coincidence, but the timing is at minimum interesting. Multiple visible celestial events draw attention upward, while an invisible interstellar object and critical digital infrastructure both enter their own blind windows. I want to emphasize that Comet Lemon, Comet Swan, and the Orionid meteor shower are completely natural phenomena following predictable celestial mechanics. There's no suggestion these events are anything other than what they appear to be. The point here is about attention and where it flows. Visible, accessible phenomena naturally attract our focus. Hidden or technical phenomena require deliberate effort to monitor and understand. When the visible and the hidden both become active simultaneously, our attention defaults to what we can directly perceive. What happens in the gaps in the spaces we're not watching remains uncertain until we specifically investigate. Part 6. Sagittarius traffic lanes and hidden corridors. Let's expand the frame beyond this single event and ask a larger question. Could the galaxy itself have a structure that influences how objects move through it? Not just the obvious gravitational wells of stars and planetary systems, but preferential corridors, streams, or highways that channel interstellar traffic along specific paths. This idea might sound like science fiction, but there's legitimate physics behind it. The galaxy isn't uniformly distributed mass. It has structure density variations, currents of dark matter, stellar streams where groups of stars move together, and gravitational potentials that guide the motion of objects over enormous timescales. 3I Atlas entered our solar system from the approximate direction of Sagittarius toward the galactic center. That's the direction where the supermassive black hole at the heart of our galaxy resides, along with the densest concentration of stars in the Milky Way. Objects coming from that direction have traveled through the most gravitationally complex region of the galaxy, where stellar encounters are more common and dynamical interactions more frequent. If any part of the galaxy could act as a source or channel for ejected objects, the central regions would be a prime candidate. Dense stellar populations mean more close encounters, which means more opportunities for objects to be flung onto escape trajectories that send them wandering through interstellar space. Recent studies have been mapping the galaxy's gravitational structure with increasing precision. Surveys like GIA, which measures the positions and velocities of billions of stars, have revealed stellar streams, groups of stars that were once part of globular clusters or dwarf galaxies, but have been torn apart by tidal forces and stretched into long filaments. These streams follow specific orbital paths determined by the galaxy's gravitational potential. Dark matter, the mysterious substance that outweighs ordinary matter by 5-1 but interacts only through gravity, also has structure. Simulations show that dark matter forms halos, filaments, and voids, creating a gravitational scaffolding that influences how everything else moves. Could interstellar objects follow similar paths? Think about how information moves on Earth. The internet isn't a uniform mesh where every point connects equally to every other point. It has backbone routes, major fiber optic cables, and exchange points where traffic concentrates. Data flows along these highways because they're the most efficient paths to places where infrastructure is densest and bandwidth highest. Similarly, ocean shipping doesn't scatter randomly across every square mile of ocean. Ships follow established routes optimized for distance, currents, and port locations. Even air traffic has structured corridors, jet streams, and approach paths. Aircraft don't wander arbitrarily through three-dimensional space. The galaxy might work similarly on much larger scales. If interstellar objects are frequently ejected from the central regions due to stellar encounters, and if the galaxy's gravitational structure channels them along certain paths as they disperse outward, then you might expect to see an overrepresentation of objects arriving from specific directions. 3I Atlas coming from Sagittarius could be following one of these corridors, a gravitational highway that funnels objects from the core regions outward through the galactic disk. Other interstellar visitors arriving in the future might show similar directional clustering if this hypothesis is correct. Of course, we have to be cautious about selection bias. We've only identified 3 confirmed interstellar objects ever. That's an absurdly small sample size from which to draw conclusions about galactic structure or preferential directions. Oumuamua came from the direction of Lyra. Borisov came from a direction roughly toward Perseus. 3I Atlas from Sagittarius. 3 data points don't make a pattern, at least not one you can confidently generalize. It's entirely possible that interstellar objects arrive from random directions, and we're just seeing the first few examples of what will eventually reveal itself as a uniform distribution. The apparent Sagittarius connection might mean nothing more than we happen to discover this particular object first among many that could come from anywhere. But let's consider the implications if there actually are preferential corridors for searches for interstellar visitors. This would be valuable information. Rather than scanning the entire sky with equal priority, you could focus on regions where objects are more likely to appear. Resources are always limited. Telescope time is precious. Survey programs have to make choices about where to point and how long to look. If certain directions are genuinely more productive for finding interstellar objects, that's information worth having. It would change how we design detection programs and allocate observation time. There's also the question of who or what uses these corridors. Natural comets and asteroids certainly objects ejected by stellar encounters or planetary interactions sent wandering through the galaxy. But if a corridor exists, anything traveling through interstellar space would find the same route advantageous. The concept applies regardless of whether we're talking about rocks or probes. A gravitational highway is just geometry and physics. It doesn't care what's using it. So if an advanced civilization wanted to send objects through the galaxy, they might naturally utilize the same corridors that natural objects follow, either intentionally or simply because those paths are the most efficient. Now, connecting this to the AWS outage might seem like a stretch. What does galactic structure have to do with cloud infrastructure? The connection is more conceptual. The concept applies regardless of whether we're talking about rocks or probes. A gravitational highway is just geometry and physics. It doesn't care what's using it, so if an advanced civilization wanted to send objects through the galaxy, they might naturally utilize the same corridors that natural objects follow, either intentionally or simply because, just as a disruption in a galactic corridor might affect the distribution of interstellar objects, both systems, cosmic and digital, demonstrate how centralization creates vulnerability. When traffic concentrates along specific paths or through specific nodes, those locations become critical points of failure. Take one out, and the entire network feels the impact. The parallel extends to visibility and monitoring. In our galaxy, we can only observe objects when they pass through regions where our telescopes have clear lines of sight. Most of interstellar space is effectively invisible to us. We detect objects when they enter our solar system, but their journeys through the galaxy before arrival remain largely mysterious. Similarly, in digital infrastructure, we can monitor the nodes and connections we control, but vast portions of the network remain opaque to any single observer. Data passes through systems owned by different entities, crosses international boundaries, and flows through infrastructure we can't directly inspect. We see what enters and exits our domain, but the full path remains partially hidden. If someone or something wanted to move through either system undetected, understanding the corridors and their blind spots would be essential. In the galactic case, timing your arrival to coincide with solar conjunction masks your passage through the most observable phase. In the infrastructure case, disrupting a critical hub degrades monitoring across dependent systems, creating opportunities for undetected action. Whether these patterns connect to each other or simply reflect common principles of how complex systems work is an open question. But the conceptual similarity is striking enough to warrant consideration. What this means for future investigations is clear. If we want to find more interstellar visitors, we should pay special attention to potential corridors, regions where galactic structure might funnel objects toward us. If we want to secure our digital infrastructure, we need to reduce centralization and create redundancy so that no single hub's failure can cascade globally. Both approaches require understanding structure, mapping the hidden architecture that determines how objects and information flow through their respective systems. Part 7. Data suppression, classified orbits, and cloud black boxes. There's another dimension to this story that makes definitive answers difficult, the question of what information exists but remains unavailable. In both astronomy and cloud infrastructure, not all data is public. Some observations are embargoed for scientific reasons. Some details are withheld for competitive advantage, and some information is classified for national security. When major events occur, the gaps in public knowledge become more apparent and frustrating. We know something happened, but the details that would let us understand exactly what and why remain locked behind closed doors. Inside proprietary systems. For 3I Atlas, observers have noted delays in releasing certain orbital refinements in spectroscopic data. This isn't necessarily sinister. Astronomy operates on a publication model where researchers who make discoveries or observations typically get first rights to analyze and publish their findings before data becomes public. Embargoes protect the scientific process, ensuring that those who do the work get credit for their discoveries, rather than having their results scooped by others using their data. Delays of weeks or months are normal and expected. What raises eyebrows is when delays extend beyond typical timeframes, when specific data types remain unavailable, or when the reasoning for withholding information seems unclear. Some precedents exist in recent astronomy. When the James Webb Space Telescope began observing exoplanet atmospheres, certain spectra were subject to extended embargoes, while teams verified their analysis methods and prepared publications. Similarly, a mission to a metal-rich asteroid has experienced data release delays as scientists work through complex measurements. These examples show that data suppression, if we want to call it that, happens for legitimate scientific reasons. But they also show that information can be restricted in ways that limit public understanding and independent verification. When something as unusual as an interstellar object enters solar conjunction at its moment of highest activity, any delays in data release naturally fuel speculation about what might be hidden. In the case of 3I Atlas, the conjunction itself creates a literal information gap. For the period when the object is behind the Sun, there's simply no data to release because no observations are possible from Earth. Space-based telescopes in different orbits might theoretically maintain some visibility depending on their positions. But most of our observation infrastructure is Earth-based or orbits close to Earth, meaning it shares our blind spot. When the object emerges from conjunction, observers will collect new data, but what happened during the invisible period will remain unknown unless indirect evidence reveals it. Post-conjunction trajectory analysis might show changes that imply what forces acted during invisibility, but direct observation of the crucial perihelion phase is impossible. The cloud infrastructure equivalent is equally opaque. When AWS experiences a major outage, their public statements typically provide high-level explanations. Technical failures in specific services elevated error rates, resolution timelines. What they don't provide, understandably from a competitive and security perspective, are detailed forensic logs that would allow outsiders to fully reconstruct what happened. Root cause analyses are conducted internally. If vulnerabilities were exploited, that information is not publicly disclosed. If the outage cascaded from a specific misconfiguration or code bug, the details remain proprietary. Users and dependent businesses get enough information to understand the impact and timeline, but the deep technical details stay inside Amazon systems. This creates what we might call a black box problem. We can observe inputs and outputs, but the internal mechanisms remain hidden. For 3I Atlas, we can observe its trajectory before conjunction and after, but not during. For AWS, we can see that services went down and later came back up, but not exactly what failed internally, or whether any malicious activity occurred during the chaos. In both cases, the entities with the most information, observatories and cloud providers respectively, have legitimate reasons to control how and when they release details. But that control limits public understanding and makes it difficult to distinguish between normal operational opacity and deliberate information suppression. National security adds another layer. If an interstellar object showed characteristics suggesting an artificial origin, would that information be immediately released, or would it be classified while governments determined how to respond? If cloud infrastructure were compromised by a state-sponsored attack, would the full details be disclosed, or would certain aspects be withheld to avoid revealing defensive capabilities or intelligence sources? These aren't hypothetical questions. Information has been classified for less. The boundary between public science and national security is fuzzy when topics touch on potential threats or advanced technology. The risk of this opacity is that it fuels speculation and mistrust. When people know something happened but can't get clear answers about what or why, they fill the gaps with theories some more plausible than others. The lack of transparency becomes evidence of conspiracy in some minds, even when the actual reasons for withholding information are mundane. This is a genuine dilemma. Complete transparency could reveal vulnerabilities or compromise. Competitive advantages, but excessive secrecy breeds suspicion and makes it harder to build public trust. In astronomy, the trend has been toward more openness. Citizen science projects allow amateurs to participate in discovery. Data from major surveys increasingly becomes public after reasonable embargo periods. Independent observers can verify published results and conduct their own analyses. This openness strengthens science by enabling broader participation and independent checking, but gaps remain particularly for observations requiring specialized equipment or for objects that become invisible during critical phases. Three-Eye Atlas's blind passage is a natural gap, not one created by policy, but it has similar effects. We're simply unable to observe during the most interesting period, and no amount of transparency can fix that fundamental limitation. For digital infrastructure, transparency is improving, but remains far behind astronomy. Cloud providers share high-level metrics about uptime and performance, but detailed operational data stays internal. Security researchers sometimes publish findings about vulnerabilities, but coordinated disclosure practices mean delays between discovery and public release. When major incidents occur, post-mortems provide some information but rarely complete forensic details. The balance between operational security and public accountability continues to evolve, with different providers taking different approaches. What we're left with is uncertainty. Did Three-Eye Atlas do anything unusual during conjunction? We won't know until post-conjunction observations reveal changes or anomalies. Did the AWS outage involve more than just technical failure? We likely won't ever know unless someone with access to internal logs decides to share that information publicly. The gaps in our knowledge aren't necessarily evidence of conspiracy or suppression, but they do create space for speculation that's difficult to definitively counter without access to the missing information. Part 8. Lobe the Probe Hypothesis and Cloud Warfare. If you've been following discussions about interstellar objects in recent years, you've almost certainly encountered the name Avi Loeb. He's a Harvard astrophysicist with an impressive publication record and a willingness to entertain hypotheses that many of his colleagues find too speculative. Loeb first gained widespread public attention with his arguments about Oumuamua, the first confirmed interstellar visitor. He suggested that based on the object's unusual acceleration and elongated shape, we should seriously consider the possibility of an artificial origin, perhaps a light sail or probe sent by another civilization. While the scientific community largely rejected this interpretation in favor of natural explanations like outgassing or unusual composition, Loeb's arguments captivated the public imagination and sparked essential discussions about how we would recognize artificial objects if they visited our solar system. Now, with Three-Eye Atlas, Loeb has again raised the probe hypothesis. He points to the timing of solar conjunction coinciding with perihelion, the unusual chemistry with high carbon dioxide and nickel content, the forward glow observed by Hubble, and the object's trajectory from the direction of Sagittarius. Taken together, Loeb argues that these characteristics warrant serious consideration that Three-Eye Atlas might be something other than a natural comet. Loeb's position isn't that it definitely is artificial, but that we should keep that possibility open and look for evidence to confirm or rule out the hypothesis. In his view, dismissing the probe hypothesis outright is unscientific, a form of bias that prevents us from discovering something potentially revolutionary. The probe hypothesis in its most developed form goes something like this. An advanced civilization might send exploratory probes through the galaxy, possibly millions of them, over long periods of time. These probes could be disguised as natural objects to avoid detection, or they might simply resemble comets because both are small, icy bodies traveling through space. A probe approaching a star system would want to gather maximum information during its passage. The perihelion window, when the probe is closest to the star and moving fastest, would be ideal for performing maneuvers, deploying sub-probes to study planets, or conducting observations requiring proximity. If the probe's trajectory naturally places it behind the Sun during perihelion from the perspective of the system's inhabited planet, that's actually advantageous. It allows the probe to conduct its activities without being directly observed by the civilization it's studying. The parallels to cyber warfare and intelligence operations are obvious enough that Loeb and others have drawn them explicitly. In digital conflict, advanced persistent threat APT actors often establish a presence in a network and wait for optimal moments to act. They might sit dormant for months or years, gathering information and mapping systems before executing their primary objectives during windows of reduced monitoring or heightened chaos. A major infrastructure outage creates exactly that kind of opportunity. Defenders are focused on restoration rather than detection. Monitoring systems are degraded, and the noise of the crisis masks subtler anomalies that might otherwise trigger alerts. If you were designing an interstellar probe and wanted to study a solar system with an emerging technological civilization, you'd face similar operational considerations. How do you gather information without revealing your presence? How do you conduct activities without triggering defensive responses? Timing your most active phase to coincide with natural blind spots makes strategic sense. The civilization you're studying loses direct observation capability precisely when you need to maneuver or deploy assets. By the time they can see you again, your activities are complete, and your new trajectory is established. Critics of Loeb's approach, and there are many in the astronomical community, argue that he's engaging in speculation beyond what the evidence supports. They maintain that natural explanations for 3I Atlas, his characteristics exist, and should be preferred until proven insufficient. Unusual chemistry could result from formation conditions in a different stellar system. Forward glows occur in natural comets through well-understood mechanisms. The timing of conjunction with perihelion is determined by orbital mechanics, not intelligence. Suggesting alien probes based on ambiguous data risks, sensationalizing science and misleading the public about what we actually know versus what we're guessing. These critiques have merit. The history of astronomy is full of examples where unusual observations initially seemed to suggest exotic explanations, but ultimately yielded more mundane interpretations. Pulsars, when first discovered, were briefly called LGM little green men, because their precisely timed radio pulses seemed too regular to be natural. They turned out to be rapidly rotating neutron stars, exotic certainly, but not artificial. Fast radio bursts, mysterious millisecond flashes from deep space sparked speculation about alien signals, but now appear to be natural astrophysical phenomena, possibly from magnetars. The default assumption in science is that natural causes are more likely, with artificial or exotic explanations requiring extraordinary evidence. But Loeb's counter-argument is also worth considering. If we automatically default to natural explanations and never seriously investigate artificial possibilities, we might miss the most important discovery in human history. The first genuine detection of alien technology won't announce itself with obviously artificial signatures. It will probably be ambiguous, showing characteristics that could be natural but might not be. If we always choose the natural interpretation without rigorous investigation of alternatives, we'll never find artificial objects even if they're visiting regularly. His advocacy isn't for accepting the probe hypothesis on current evidence, but for taking it seriously enough to look for confirming or disconfirming evidence rigorously. The media and public perception angle matters here. When a prominent Harvard scientist suggests that an interstellar object might be alien technology, that's a story that generates attention and clicks. News coverage amplifies the speculation often without proportionally amplifying the scientific skepticism. This creates a feedback loop where the probe hypothesis gets more public awareness than its evidential support warrants. Some scientists worry this damages public understanding of how science works and what standards of evidence mean. Others argue that engaging public interest in space exploration and the search for life is valuable even if specific claims don't pan out. Tying this back to the AWS outage, the parallel questions become clear. Just as Loeb questions whether we should accept the natural object explanation for 3I Atlas without deeper investigation, we might question whether we should accept the technical failure explanation for the cloud disruption without deeper investigation. Was it really just elevated error rates and configuration issues, Or could there have been a deliberate component, an attack or sabotage that exploited the infrastructure at a moment of reduced visibility? The timing coincidence doesn't prove a connection, but it raises the question of whether we're looking hard enough for non-obvious explanations. Loeb co-founded the Galileo Project, an initiative aimed at systematically searching for potential techno-signatures, including unusual objects passing through our solar system. The project deploys telescopes specifically designed to detect and track objects that might have artificial characteristics, looking for things that don't fit natural patterns. Whether 3i Atlas warrants that level of scrutiny depends on who you ask. For Loeb and like-minded researchers, every interstellar visitor deserves careful investigation for possible artificial origin. For most astronomers, natural explanations remain far more likely, and speculative alternatives just distract from solid science. What makes this particular case interesting is the visibility gap. If 3i Atlas does something revealing during conjunction, we won't see it directly. We'll only detect indirect evidence afterward. Anomalies in trajectory or composition that require explanation. That's not ideal for testing the probe hypothesis. You want continuous observation to catch unambiguous artificial behaviors in real time. A gap in observation, especially when coinciding with the object's most dynamic phase, makes definitive conclusions harder, regardless of which hypothesis you favor. Part 9: Energy Maneuver, Windows, and Hidden Burns. Let's talk about energy and orbital mechanics, the physics that governs how objects move through space, and what's possible during different phases of a trajectory. This might seem technical, but it's crucial for understanding why the conjunction and perihelion timing matters so much, both for natural comets and hypothetical probes. The core concept is something called the Obath effect, named after Hermann Obath, one of the founding fathers of rocketry. The Obath effect tells us that if you want to change an object's trajectory most efficiently, you do it when the object is moving fastest. Here's why this works. Kinetic energy, the energy of motion, depends on velocity squared. Double your speed, and your kinetic energy quadruples. When you apply thrust to change your velocity, the effect on your total energy depends on your current speed. If you're moving slowly, and you add 1 km/s to your velocity, the energy change is relatively small. If you're already moving at 10 km, and you add 1 more km/s, the energy change is much larger. This might seem counterintuitive. You're adding the same velocity change either way, but the energy effect is vastly different because energy scales with velocity squared. For an object orbiting the Sun, the fastest point in the orbit is perihelion, the closest approach. This is where gravitational acceleration has been pulling on the object most strongly, converting gravitational potential energy into kinetic energy. For 3i Atlas, perihelion occurs at approximately 1.36 astronomical units from the Sun around October 29, 2025. At that point, the object is moving faster than at any other point in its trajectory through our solar system. If you wanted to perform a maneuver, a propulsive burn, to change velocity or direction, perihelion is the optimal moment. The same thrust that would produce a modest trajectory change elsewhere in the orbit produces a much larger change at perihelion. Natural comets show something analogous. As they approach the Sun, solar heating vaporizes ice on the surface, creating jets of gas and dust. These jets act like natural rocket engines, applying force to the comet. If the jets are asymmetric, coming more from one side than the other, they create non-gravitational acceleration that changes the comet's trajectory. This happens naturally, no intelligence required, but the effect is largest near perihelion, when solar heating is strongest, and the comet is moving fastest. Astronomers observe these non-gravitational accelerations regularly in comets. They're one reason why predicting comet trajectories precisely requires careful observation. The gravitational forces alone don't tell the whole story. You need to account for the thrust from outgassing. An artificial burn, a deliberate maneuver by a probe, would produce similar trajectory changes, but potentially with different signatures. A natural jet is driven by solar heating, so its strength correlates with distance from the Sun and the comet's rotation state. It tends to be somewhat random in direction depending on where ice deposits exist on the surface. An artificial burn could be precisely timed and directed, executing a specific trajectory correction with calculated efficiency. Distinguishing between natural and artificial would require careful measurement of the acceleration's direction, magnitude, and timing, relative to solar distance and other factors. The problem with 3I Atlas is that its perihelion maneuver window, if any maneuver occurs, happens behind the Sun from Earth's perspective. We can't watch it happen in real time. The before and after states will be observable, the trajectory as the object enters conjunction and the trajectory as it emerges. If those don't match within the uncertainties of natural outgassing, if the change is too large or in an unexpected direction, that would be evidence of something unusual. But subtle maneuvers, ones that could be explained as plausibly natural or possibly artificial, might be impossible to definitively categorize without direct observation of the event itself. Fragmentation is another possibility to watch for. If thermal stress or rotational forces cause 3I Atlas to break apart during perihelion, multiple objects will emerge from conjunction instead of one. This happens with natural comets. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before colliding with Jupiter. Comet Dyson disintegrated during its 2013 perihelion passage. If 3I Atlas fragments, that's strong evidence for natural processes. Structural failure from thermal stress is hard to fake and serves little purpose for a hypothetical probe. But controlled deployment of sub-probes would also appear as multiple objects emerging from conjunction. Distinguishing fragmentation from deployment requires analyzing the trajectories and characteristics of the resulting pieces. Post-conjunction observations will look for several signatures. First, has the trajectory changed more than natural outgassing can explain? Second, are there multiple objects where one entered conjunction? Third, has the brightness or spectroscopic signature changed in ways suggesting surface alterations or material release? Fourth, are there unusual emissions or signals that weren't present before conjunction? Each of these observations provides information about what happened during the invisible period. But interpretation won't necessarily be straightforward. Natural processes can produce a wide range of behaviors, and without direct observation, ruling out natural explanations definitively is challenging. The cybersecurity analogy continues to hold in network defense. Attackers often strike during maintenance windows or scheduled downtime when monitoring is reduced. System updates, database migrations, infrastructure changes. These create opportunities for malicious actors to move through networks with reduced risk of detection. By the time normal monitoring resumes and security teams review logs, the attacker has already accomplished their objective. The evidence exists in retrospect, but the real-time opportunity to intervene has passed. Post-incident forensics can reconstruct what happened, but prevention requires observing the attack as it occurs. For 3I Atlas, we're in a similar situation. The crucial period happens during reduced observation. Post-conjunction analysis will tell us something, but we've missed the real-time observation that would provide the clearest evidence of what actually occurred. If something artificial is happening, the timing is near perfect. If everything is natural, we've unfortunately lost observation of the most scientifically interesting phase due to unavoidable geometric alignment. Infrastructure parallels extend to the AWS outage as well. During the crisis, as services failed and systems went offline, was anything else happening in the chaos? Did threat actors use the degraded monitoring as cover for intrusion or data exfiltration? Post-outage analysis might reveal anomalies, traffic patterns that don't make sense, or data transfers that shouldn't have occurred. But real-time detection during the crisis would have been difficult even for sophisticated security operations. The noise and confusion of a major outage masks subtler signals that might otherwise trigger alerts. What we're left with is strategic ambiguity, a situation where multiple interpretations remain possible even after observation. For 3I, Atlas natural comet behavior versus probe activity might both be consistent with post-conjunction measurements. For the AWS outage, pure technical failure versus opportunistic attack might both fit the available evidence. Without complete information, without observation during the critical windows, definitive conclusions become difficult. This ambiguity isn't comfortable, but it's the reality of observing complex systems with inherent limitations in coverage and visibility. Part 10. Coincidence or choreography? Let me lay out the timeline again so we can see the pieces come together. October 20th, 2025, early morning Eastern Time. AWS US East 1 region experiences a major outage disrupting services globally. October 21, 2025. 3I Atlas enters solar conjunction, becoming invisible to Earth-based observation. October 29, 2025. 3I Atlas reaches perihelion behind the Sun at its point of maximum solar interaction and fastest velocity. The object arrives from the direction of Sagittarius toward the galactic center. Its composition shows unusual chemistry. Its trajectory includes a relatively small inclination to the ecliptic. Multiple bright comets and a meteor shower peak around the same dates, creating a visible celestial spectacle. Individually, each of these events happens. Cloud infrastructure occasionally fails at large scale despite redundancies. Interstellar objects visit our solar system on their own schedules determined by galactic dynamics. Solar conjunction is predictable from orbital mechanics. Comets and meteor showers occur naturally. Nothing about any single element is impossible, or even particularly unlikely over long enough time frames. The question is whether their simultaneous occurrence is a coincidence or indicates some form of choreography, either by human actors exploiting the timing, or by something stranger coordinating across multiple domains. Let's think about probabilities qualitatively, since we don't have enough data for rigorous statistical analysis. Major AWS outages affecting US East 1 happen perhaps once or twice per year. Interstellar objects visit the inner solar system perhaps a few times per decade based on current detection rates, though our detection capability is improving, so the true rate might be higher. Solar conjunction happens for any given object exactly once during its passage through the inner solar system, but whether that conjunction coincides with perihelion depends on orbital geometry. For 3I Atlas, the conjunction perihelion alignment is a feature of its specific hyperbolic trajectory, not something that changes. The overlap of a major infrastructure outage with an interstellar object's conjunction is on the surface unlikely. These are independent systems operating on completely different scales. One is human technology in a specific location on Earth. The other is cosmic mechanics playing out across astronomical distances. You wouldn't expect them to correlate unless something connects them. That connection could be coincidence, a genuinely random overlap that's bound to happen occasionally if you wait long enough. Or it could be coordination, either someone exploiting the cosmic timing to mask terrestrial activities, or something beyond our current understanding operating across both domains. Humans are pattern-seeking animals. This is a feature, not a bug. Our brains evolved to detect patterns because pattern recognition helps survival. The rustle in the grass might be wind, or it might be a predator. The pattern-seeking brain that assumes predator and prepares to flee survives more often than the brain that assumes wind and gets eaten. But this strength becomes a liability when we see patterns and randomness, when we connect unrelated events and construct narratives that feel compelling but aren't actually supported by evidence. Psychologists call this illusory correlation or apophenia, the tendency to perceive meaningful connections between unrelated things. So we have to ask ourselves honestly, are we seeing a real pattern here, or manufacturing one from coincidence? The honest answer is, we don't know yet. The timing is unusual enough to warrant attention. The conjunction of a cosmic event with infrastructure failure, both creating blind spots in their respective domains, is at minimum striking. But striking isn't the same as significant. Random chance produces surprising coincidences regularly. The lottery winner who dreamed the winning numbers didn't actually predict the future through some mystical connection. Among millions of players, someone's random dream will match random numbers purely by chance. The pattern emerges from the statistics of large numbers, not from a meaningful connection. However, if we shift from coincidence to choreography, the implications expand dramatically. Choreography implies planning, intelligence, intentionality. If human actors exploited the 3I Atlas conjunction timing to mask infrastructure attacks that suggest a level of sophistication and coordination between astronomical awareness and cyber operations, nation-state actors certainly have that capability. Intelligence agencies monitor all kinds of information, including astronomical events, looking for opportunities and cover. Using a cosmic blind window as timing for a terrestrial operation isn't beyond current human capability. It would require prior planning, waiting for the right moment, then executing when observation conditions align. If the choreography extends beyond human actors, if something about 3i Atlas itself connects to the infrastructure disruption, we're in radically different territory. That would require technology far beyond our current capabilities, the ability to coordinate physical objects across astronomical distances with precise timing relative to Earth-based systems. It would require knowledge of our infrastructure vulnerabilities, either through observation or through principles that apply universally to technological civilizations. This hypothesis sounds like science fiction, and maybe it is, but it's worth considering what evidence would support or refute it. What would shift you personally from coincidence to intent? This is a question worth asking yourself. For some people, the current coincidence is already suspicious enough to lean toward intentional coordination. For others, no amount of coincidence would be convincing without direct evidence of mechanism, something that shows how the events are actually linked. Scientific thinking generally demands the latter. Coincidence alone, no matter how unlikely, isn't evidence of causation. You need a mechanism, a way that one event could produce or coordinate with the other. Without that mechanism, you're just noting that two things happened at similar times. The cyber warfare parallel offers one potential mechanism. An advanced actor, human or otherwise, wanting to conduct operations on Earth without detection, could time those operations to coincide with reduced observation capability. Solar conjunction creates a cosmic blind spot. Infrastructure disruption creates a terrestrial blind spot. Acting in the overlap of those blind spots maximizes the chance of remaining undetected. This is tradecraft that current intelligence agencies understand and use. The unusual element would be coordinating terrestrial operations with cosmic geometry, which requires either extremely long-term planning or the ability to influence when events occur. If we assume coincidence instead of choreography, what does that tell us? It reveals our fragility and our observational limits without requiring any exotic explanation. Cloud infrastructure is vulnerable to failure, whether from technical problems, configuration errors, or deliberate attack. Our cosmic observation capabilities have fundamental blind spots determined by our position in space and the placement of the sun. These vulnerabilities exist independently and will occasionally overlap by pure chance. The lesson is about resilience and redundancy, about not depending too heavily on single points of failure in either technological or observational infrastructure. Philosophically, the choreography hypothesis forces us to confront our role in the universe. Are we observers watching cosmic events unfold, or are we participants in something larger that includes us, whether we realize it or not? If advanced intelligences exist and occasionally interact with or observe developing civilizations like ours, how would we recognize those interactions? They might not announce themselves. They might operate subtly, exploiting our blind spots, working in the gaps between our observation capabilities. We assume we would know if something extraordinary were happening, but that assumption might be naive. Subtlety and misdirection are exactly what you'd expect from advanced intelligence operating on its own timeline and agenda. The question isn't necessarily answerable with current evidence. We need post-conjunction observations of 3i Atlas to see if anything unusual occurred. We need deeper forensics on the AWS outage to determine if technical failure fully explains the event. We need to watch for patterns in future incidents, whether similar coincidences occur, or whether this was genuinely a one-time random overlap. Science advances through observation and testing, not through speculation alone. But speculation serves a purpose. It identifies possibilities worth investigating, questions worth asking, and observations worth making carefully. Part 11. Quantum Communication Breakthroughs. While all of this was unfolding, another development in October 2025 deserves attention, not because it directly connects to 3i Atlas or the AWS outage, but because it illustrates a broader theme running through our story. The theme of invisibility of communication and movement happening in ways that evade traditional detection. In October 2025, multiple research groups announced record-setting achievements in satellite-based quantum entanglement and quantum communication. These experiments demonstrated the ability to maintain quantum states across continental distances, establishing links that are theoretically immune to classical eavesdropping. The technology is still experimental, not yet deployed at scale, But the breakthroughs represent a significant step toward communication networks that operate in fundamentally invisible ways. Let me explain what quantum entanglement means and why it matters for communication. In quantum mechanics, particles can be entangled, linked in such a way that measuring one instantly affects the state of the other regardless of the distance between them. This isn't communication in the traditional sense. You can't use this entanglement to send information faster than light, but you can use it to establish secure communication channels. When two parties share entangled particles, they can use measurements of those particles to generate encryption keys that are provably secure. Any attempt to intercept or measure the quantum states destroys the entanglement, immediately revealing the presence of an eavesdropper. Traditional communication, everything from ancient signal fires to modern fiber optics, works by encoding information in some physical carrier and transmitting that carrier from sender to receiver. Light pulses in fiber radio, waves through air, electrons through copper wire. An eavesdropper with access to the transmission medium can intercept the signal without the communicating parties knowing. Encryption makes the intercepted data useless without the key, but the act of interception itself remains invisible. Quantum communication changes this. The quantum states used to establish the encryption key cannot be copied or intercepted without detection. The physics itself provides security, not just mathematical complexity. The October 2025 breakthroughs demonstrated that this technology can work over satellite links spanning thousands of kilometers. Previous experiments had shown quantum entanglement over shorter distances or in controlled laboratory settings. Scaling up to continental distances through atmospheric turbulence and across moving satellite platforms represents a major engineering achievement. The researchers involved describe it as a crucial step toward a future quantum internet, a communication network where privacy is guaranteed by physics rather than just cryptographic algorithms. Why does this matter for our larger story? Because it represents another domain where critical activities can become invisible to classical observation, just as 3I Atlas hides behind the sun during conjunction. Invisible to our telescopes, quantum communication channels hide from classical interception by operating through mechanisms that resist measurement. An advanced civilization with mature quantum communication technology could coordinate across vast distances without producing signals detectable to civilizations still using classical electromagnetic transmission. We're just beginning to develop these capabilities ourselves, barely achieving reliable entanglement over satellite distances. A civilization even a few centuries more advanced might have perfected technologies that are completely invisible to our current detection methods. This connects to the broader question of what we're not seeing. Our search for techno-signatures, evidence of advanced civilizations elsewhere in the galaxy, focuses largely on signals we know how to detect: radio transmissions, optical laser pulses, megastructures that alter stellar spectra. These are the kinds of technologies we use or can imagine using, so we look for evidence of them. But what if advanced civilizations move beyond these observable technologies relatively quickly in their development? What if quantum communication, or something even more exotic that we haven't discovered yet, becomes the preferred method for most significant communication? We'd be looking for signals that nobody's sending anymore, like trying to find modern civilization by scanning for smoke signals. The infrastructure angle also matters. Our digital networks are increasingly concerned with quantum security because of the threat from quantum computers. A sufficiently powerful quantum computer could break current encryption algorithms, rendering most of our secure communication insecure overnight. Transitioning to quantum-resistant encryption and ultimately to quantum communication networks is a priority for maintaining security in a future where quantum computing becomes widespread. But this transition happens gradually, and during the transition period, systems are vulnerable. An attacker with quantum computing capability and knowledge of which systems haven't yet upgraded their encryption has a window of opportunity to intercept and decrypt communication that the targets believe is secure. Could this play into the AWS outage scenario? It's speculative but worth considering. If an advanced actor, whether human or otherwise, possessed communication or computing technology beyond our current capabilities, they could potentially coordinate activities invisibly to our monitoring systems. The infrastructure disruption might have served multiple purposes: degrading defensive capabilities, creating chaos that masks other activities, and potentially testing response capabilities to map out network structure and resilience. While this is happening, communication about the operation could occur through channels we simply can't monitor, because we lack the technology to even detect them. I want to emphasize that there's no evidence connecting quantum communication breakthroughs to either the AWS outage or 3i Atlas. The timing is coincidental as far as we know, but the conceptual parallel is instructive. As technology advances, the gap between what's happening and what we can observe grows larger. Invisibility isn't just about physical location being behind the sun or inside encrypted networks. It's also about operating through mechanisms that our detection methods can't access. An object using technology we don't understand might be completely invisible even when it's right in front of us. The October 2025 quantum communication achievements remind us that we're still early in understanding what's possible. Technologies that seem exotic and experimental today might be commonplace in decades or centuries. If we're trying to detect evidence of civilization centuries or millennia ahead of us, we should expect them to operate in ways we can barely imagine. The fact that we don't see obvious signs might not mean they're not there. It might mean we're looking in the wrong spectrum, listening at the wrong frequencies, searching for technologies they've long since surpassed. Part 12. AI finds what we didn't see. In January of 2025, a team of researchers at the University of Toronto published something extraordinary. They'd taken a deep learning algorithm fed it years of archived gravitational wave data from LIGO and Virgo and set it loose to hunt for patterns. What came back shocked them. The AI had identified 17 previously undetected merger events, black holes, and neutron stars colliding in the darkness of space. Events that human analysts had completely missed. The signals had been there all along, buried in the noise, waiting for something with enough patience and precision to notice them. We had been blind to our own data. This discovery wasn't just a technical achievement, it was a philosophical one. For years, scientists had assumed they were extracting everything meaningful from these archives. That human expertise, combined with traditional algorithms, was sufficient to catch every cosmic whisper. The gravitational wave detectors are among the most sensitive instruments humanity has ever built, capable of measuring distortions in space-time smaller than a proton. Yet despite all that sensitivity, despite all that expertise, we were still missing things. The AI saw what we couldn't because it approached the problem differently. It didn't look for what we expected. It looked for everything. Machine learning excels at this kind of work because it operates without preconceptions. A human analyst brings assumptions to data, expectations shaped by theory and experience. We look for specific waveforms, particular frequency patterns, signatures that match our models. An AI, by contrast, can be trained to recognize deviations from baseline noise without caring whether those deviations fit our expectations. It treats every data point as potentially meaningful, sifting through millions of measurements to find the anomalies that might represent real events. In the case of gravitational waves, that meant identifying merger signals that were either too faint, too brief, or too distorted by noise for conventional methods to catch. But here's where it gets complicated. Machine learning doesn't just find hidden signals, it also finds false positives. An algorithm trained to spot anomalies will spot anomalies whether they're genuine cosmic events or just statistical flukes. The 17 mergers the Toronto team found weren't immediately accepted by the broader scientific community. Each one had to be verified through painstaking analysis, cross-referenced against other data sources, tested for consistency with known physics. Some of them might still turn out to be noise masquerading as signal. The AI gave us candidates, not conclusions. It opened doors, but humans still had to walk through them carefully. This is the tension at the center of algorithmic discovery. On one hand, these tools can reveal patterns we would never find on our own, connections too subtle or too complex for human cognition to grasp. On the other hand, they can amplify our biases, generate spurious correlations, or simply overwhelm us with false leads. The hype around AI and science often glosses over this reality. Every week brings new headlines about machine learning revolutionizing medicine, climate science, materials, research, astronomy. Some of those claims are legitimate. Many are exaggerated. The difference between a genuine breakthrough and algorithmic noise often comes down to how rigorously the results are validated. So why does hidden data matter? Because our understanding of the universe is limited not just by what we can observe, but by what we can extract from what we've already observed. There are decades of astronomical archives sitting on servers around the world, petabytes of telescope images, spectroscopic measurements, radio signals, X-ray data. Most of it has been analyzed once, filed away, and forgotten. But those archives are snapshots of moments that will never occur again, cosmic events that unfolded billions of years ago, leaving their traces in the light that reached Earth at that particular instant. If we missed something the first time, if our tools weren't sophisticated enough, or our questions weren't sharp enough, that information might be lost forever unless we go back and look again with new eyes. Now think about 3I Atlas. Think about that blind window in early October when the interstellar object 3I Atlas was passing behind the sun, hidden from our view. The telescopes were tracking it right up until solar conjunction made observation impossible, and they'll pick it back up when it emerges. But what if something happened during that window? What if the object changed course, ejected material, emitted a signal, or did something that would have been visible to our instruments if only the sun hadn't been in the way? We wouldn't know, not immediately, but the data doesn't just vanish. Other instruments might have caught indirect evidence, radio telescopes not pointed at the sun's space-based sensors monitoring different wavelengths, gravitational wave detectors picking up disturbances we haven't yet learned to interpret. The information might be there, scattered across different archives, waiting for someone or something to connect the dots. And then there's the outage. Amazon Web Services went dark for hours on October 20th, 2025, taking with it not just websites and apps, but also data collection systems, cloud-based analysis pipelines, remote monitoring stations. Scientific instruments around the world rely on cloud infrastructure to store and process their observations. When AWS fails, data doesn't just stop flowing, it gets delayed, buffered, sometimes lost entirely. Logs that would normally be uploaded in real time get cached, locally creating gaps in the continuous record. Those gaps can be filled in later once systems recover, but the reconstruction isn't perfect. Timestamps get fuzzy, sequences get scrambled, and in rare cases, anomalies that would have triggered immediate alerts instead get buried in the backlog, noticed only weeks or months later when someone goes digging through archived logs. This is where AI becomes crucial. The same machine learning techniques that found those 17 gravitational wave mergers could potentially identify patterns in the data collected around the 3I Atlas conjunction and the AWS outage. Maybe there's nothing to find. Maybe the object behaved exactly as predicted, and the outage was just a coincidence, just infrastructure stress and bad timing. But if there's a connection, if something unusual happened during that window, we might not see it until an algorithm trained to spot anomalies in multi-source data tells us where to look. The human eye can't scan petabytes of sensor logs looking for subtle correlations. Machine learning can, yet we have to be careful. The temptation to let AI tell us what's real is powerful, especially when dealing with vast data sets and complex phenomena we don't fully understand. But algorithms can't replace judgment. They can't replace the slow, tedious work of verification, the cross-checking against independent sources, the healthy skepticism that separates science from speculation. The 17 gravitational wave mergers are still being debated. Some might be real, some might not. What matters is that we found them, that we're asking the question, that we're not assuming we've already extracted everything worth knowing from our data. Because the evidence of what happened during that blind window might already exist scattered and overlooked, waiting for the right tool to make it visible. And if we've learned anything from algorithmic discovery, it's that the universe hides secrets in plain sight encoded in data we thought we'd already understood. The question isn't whether AI can find what we missed. The question is whether we're ready for what it might show us. Part 13. Solar storms and infrastructure risk. The sun is waking up. In mid-October 2025, the National Oceanic and Atmospheric Administration NOAA Space Weather Prediction Center issued an alert that caught the attention of infrastructure managers around the world. Solar Cycle 25, which began in 2019, is approaching its maximum activity phase, and forecasters are predicting an increased likelihood of G3 and G4 class geomagnetic storms over the coming months. These aren't abstract scientific classifications. They're warnings that the sun might be about to throw something at us. And when the sun throws things at Earth, our technology doesn't always survive the impact. A coronal mass ejection CME is exactly what it sounds like: the sun's outer atmosphere. The corona occasionally erupts, hurling billions of tons of magnetized plasma into space at speeds up to 3 million km/h. When one of these eruptions happens to be aimed at Earth, the plasma wave takes anywhere from 15 to 18 hours to arrive. When it does, it slams into Earth's magnetic field, compressing it, distorting it, sending cascades of charged particles spiraling down toward the poles. That's what causes auroras, those shimmering curtains of green and red light that dance across the Arctic and Antarctic skies. Beautiful to watch, but dangerous for infrastructure. The problem isn't the light. The problem is the electromagnetic induction. When charged particles from a coronal mass ejection interact with Earth's magnetic field, they create rapidly fluctuating magnetic fields in the upper atmosphere. Those fluctuations induce electrical currents in any long conductor, anything that stretches across distances, and can act as an unintentional antenna. Power lines, pipelines, undersea cables, railway tracks. These geomagnetically induced currents can overload transformers, trip circuit breakers, corrode pipeline infrastructure, and in extreme cases cause permanent damage to electrical grids. It's not theoretical. It's happened before. On March 13, 1989, a coronal mass ejection struck Earth and triggered a geomagnetic storm powerful enough to collapse the entire Hydro-Quebec power grid. 6 million people lost electricity in 90 seconds. Transformers melted. Circuit breakers failed. The province went dark for 9 hours while engineers scrambled to restore power. That same storm caused auroras visible as far south as Texas, and Florida disrupted satellite operations and knocked out radio communications across North America. It was a G5 storm, the most severe classification, and it demonstrated just how vulnerable modern infrastructure is to solar fury. We got lucky in 1989. The storm could have been worse. The next one might be, and satellites are even more vulnerable. A coronal mass ejection doesn't just affect Earth's surface infrastructure. It floods near Earth's space with high-energy particles that can damage solar panels, degrade electronics, and disrupt communications. In extreme cases, satellites can lose orientation control, suffer memory errors, or fail completely. During strong geomagnetic storms, satellite operators often shut down non-essential systems and put spacecraft into safe mode, sacrificing operational capability to protect hardware. GPS signals degrade. Communication satellites go offline. Weather monitoring stops. The infrastructure we take for granted, the invisible web of satellites providing navigation data relay. Earth observation becomes unreliable when the sun gets angry. Now consider the timing. On October 20, 2025, Amazon Web Services, AWS, suffered a major outage. That same week, 3I Atlas entered solar conjunction, hidden behind the sun from Earth's perspective. And that same month, NOAA warned of heightened geomagnetic storm risk. Could the outage have been caused by a solar event? It's a tempting connection, the kind of coincidence that feels too convenient to be random. But when we examine it closely, the link starts to fall apart. Data centers are not particularly vulnerable to geomagnetic storms. They're located far from the poles where geomagnetically induced currents are strongest. They're powered by regional electrical grids with multiple redundancies and surge protection. They're shielded from electromagnetic interference by their own construction concrete and steel buildings designed to maintain stable operating conditions. A coronal mass ejection strong enough to disrupt AWS's Virginia data center would almost certainly have caused widespread power grid failures across the entire mid-Atlantic region. It would have been obvious. There would have been reports of transformer damage, rolling blackouts, and communication outages far beyond a single cloud provider. None of that happened. The outage was isolated to AWS infrastructure, which suggests a technical or possibly cyber-related cause, not a solar event. But that doesn't mean solar storms are irrelevant to the story, because the conjunction of 3I Atlas happened to coincide with a period of heightened solar activity. And that creates an interesting scenario. When an interstellar object passes behind the sun, we lose the ability to observe it directly. But we also lose the ability to observe the sun's near environment from certain angles. If something happened during that window, if there was unusual solar activity, or if the object interacted with the sun's magnetic field in some way, we might not have the full picture. And if that same period happened to see a major infrastructure failure on Earth, even one unrelated to space weather, it creates a narrative vacuum that speculation rushes to fill. The real vulnerability isn't the sun directly attacking our cloud infrastructure. The real vulnerability is the cascading failure that happens when multiple systems become unreliable at once. Imagine a scenario where a G4 geomagnetic storm disrupts satellite communications while simultaneously causing voltage fluctuations in regional power grids. Data centers switch to backup power. Internet traffic gets rerouted through alternate pathways. Network congestion increases. And then in the middle of all that stress, a technical failure or a cyber attack targets a major cloud provider. The storm didn't cause the outage, but it created conditions where the outage became more likely, where redundancies were already strained, where response times were slower because everyone was dealing with multiple problems at once. This is how infrastructure fails in the real world, not through single catastrophic events, but through the accumulation of stresses that interact in unexpected ways. The 1989 Quebec blackout wasn't just caused by the geomagnetic storm. It was caused by the storm hitting a grid that was already operating near capacity in winter when demand was high and backup options were limited. The system was fragile and the storm found the fracture point. Modern infrastructure is more complex and in some ways more resilient, but it's also more interdependent. When one system fails, it pulls on everything connected to it. So when we ask whether the sun could have played a role in the October 20th outage, the answer is both no and maybe. No, because there's no evidence of a direct solar impact on AWS data centers. Maybe because heightened solar activity during that period might have contributed to the general stress on interconnected systems in ways we don't yet understand. The sun hides 3I Atlas during conjunction, making the object unobservable. Ironically, the sun itself can disrupt the very infrastructure we rely on to monitor space, to coordinate observations, to share data. The threat isn't just cosmic, it's local. It's our own star doing what stars do, and we're scrambling to protect technology that was never designed for the environment it now operates in. The October 2025 forecast from NOAA is a reminder that we live in a solar system, not a vacuum. Earth is constantly bathed in radiation and particles from the sun, and most of the time our magnetic field and atmosphere shield us. But during solar maximum, the sun becomes unpredictable, violent, capable of eruptions that can overwhelm our defenses. We can't control it. We can barely predict it. All we can do is watch, prepare, and hope that when the next big one comes, our infrastructure holds. Part 14. Black Hole. Echo Mapping. In February of 2025, a team of astrophysicists published a paper in Nature Astronomy that reported something remarkable. Using combined data from NASA's Chandra X-ray Observatory and the Event Horizon Telescope Radio Array, they had detected what they called space-time echoes from Sagittarius A Bowis, the supermassive black hole at the center of our galaxy. These weren't echoes in the acoustic sense. They were electromagnetic reverberations, X-rays and radio waves bouncing off the warped space-time around the black hole's event horizon, arriving at Earth with time delays that encoded information about events that happened years, decades, or even centuries ago. The researchers had essentially found a way to watch the past. The technique is called reverberation mapping, and it exploits a fundamental property of how light behaves near black holes. When material falls into a black hole, it doesn't just vanish. It spirals inward through an accretion disk, a swirling maelstrom of gas and dust, heated to millions of degrees by friction and gravitational compression. As this material approaches the event horizon, it emits intense radiation across the electromagnetic spectrum. Some of that radiation escapes directly into space, traveling in straight lines toward distant observers, but some of it gets caught in the extreme gravitational curvature near the black hole, bent and redirected sometimes multiple times before finally escaping. These photons take longer paths, arriving at Earth after their more direct counterparts, creating an echo. The delay tells you about the geometry. If you can measure the time difference between the direct light and the echo, and if you know the speed of light, you can calculate the path length, the shape of the space-time curvature that bent those photons. It's like using sonar to map an underwater cave, except instead of sound waves, you're using X-rays and radio waves, and instead of rock walls, you're mapping the fabric of reality itself. The 2025 paper reported echo delays ranging from hours to weeks corresponding to light paths bent by the intense gravity within a few dozen Schwarzschild radii of Sagittarius A's event horizon. They could see the shadow of the black hole not just in space but in time. But here's the truly strange implication. Because these echoes are delayed, they carry information about events that happened before the direct light reached us. Imagine Sagittarius A's had a sudden flare, a burst of X-rays caused by a clump of material plunging through the event horizon. We see the direct light from that flare immediately, or rather we see it 27,000 years after it happened, since that's how long it takes light to travel from the galactic center to Earth. But the echo from that same flare, the light that took a longer path, arrives hours or days or weeks later. So we're seeing the same event multiple times at different delays, like watching a recording where someone has spliced in footage from earlier in the video at random intervals. This creates an opportunity. If we can identify and separate these echoes from the direct emissions, we can reconstruct the history of activity around the black hole. We can see flares that happened months ago, variations in the accretion disk that occurred years ago, and potentially even major disruptions like a star being torn apart that happened decades or centuries ago, all encoded in the delayed light still arriving at Earth. The black hole becomes a natural archive storing information about its own past, and the bent trajectories of photons still making their way across the galaxy toward us. Now think about what this means for observation. When we watch the sky, we assume we're seeing things as they were when the light left them adjusted for light travel time. We look at a star 10 light years away and see it as it was 10 years ago. Simple, linear. But near black holes, causality gets more complicated. You can see the same event multiple times in different orders with different time delays depending on which path the light took. The path doesn't just fade away, it echoes, reverberates, persists in ways that make time itself feel less like a straight line and more like a surface with texture, with folds and wrinkles that trap and release information unpredictably. Apply this logic to 3I Atlas and the blind window. The object passed behind the sun in early October 2025, hidden from our telescopes by the glare of our own star. We lost direct observation, but that doesn't mean we've lost all information about what happened during that window. Light from the object, assuming it emits or reflects light in ways we can detect, left 3I Atlas and traveled outward in all directions. Some of that light came straight toward Earth and was blocked by the sun, but some of it might have taken indirect paths, reflecting off dust grains in the inner solar system, scattering off the solar wind, bending through gravitational lensing effects from the sun itself. Those indirect photons could arrive at Earth after the conjunction ends, delayed echoes of events we couldn't see directly. The same principle applies to the AWS outage. Digital systems generate logs, records of every transaction, every packet of data, every system event. When a major outage occurs, those logs become crucial for forensic analysis. But during the outage itself, many of those logs aren't accessible. They're cached locally, waiting for network connectivity to resume. When services recover the logs, upload in a flood a delayed echo of what happened during the blackout. Engineers sift through them looking for the root cause, the sequence of events that triggered the failure. Sometimes they find anomalies, signatures of problems that occurred hours before the outage became visible, early warning signs that got lost in the noise, until someone went back and looked for them. This is the core insight of echo mapping, whether applied to black holes or infrastructure. Hidden events leave trails. Just because we didn't see something happen in real time doesn't mean it didn't happen. And just because we can't see it directly doesn't mean we can't see its effects. The echoes and reverberations that propagate outward and eventually reach us. The challenge is learning to recognize those echoes, to distinguish them from noise, to reconstruct the original event from fragments scattered across time and space. The 2025 Sagittarius A paper is still being debated. Some researchers question whether the detected signals are true echoes, or just statistical fluctuations in the black hole's variable emission. The team is conducting follow-up observations, trying to catch more examples to build a larger data set that can test their models. It's slow work. Sagittarius A's doesn't flare on command, but if their interpretation holds up, if reverberation mapping proves to be a reliable technique, it could revolutionize how we study black holes, allowing us to probe regions of space-time that are otherwise invisible, forever hidden behind event horizons. And it might change how we think about observation itself. The idea that we only see what's directly in our line of sight is intuitive but incomplete. We see echoes, reflections, shadows, delayed signals from events that happened before we started looking. The universe is full of information, but it doesn't all arrive at once. Some of it takes detours. Some of it gets stored in unexpected places, waiting for the right instrument or the right algorithm to extract it. The blind window for 3i Atlas isn't necessarily blank. It's just encoded in ways we haven't learned to read yet. Because events in space-time don't vanish. They propagate. They echo. They leave traces. The question isn't whether the evidence exists. The question is whether we know where to look, and whether we'll recognize it when we find it. Part 15. The Mirror Turns on Us. So here we are. October 20th, 2025. A major internet outage disrupts global services. An interstellar object hides behind the sun, temporarily unobservable. Solar activity forecasts warn of heightened geomagnetic storm risks. Machine learning finds hidden signals in astronomical archives. Black hole echoes reveal events we thought were lost to time. All of these threads, all of these stories woven together into a narrative that feels too coordinated to be random, too strange to be simple coincidence. And the question sitting at the center of it all is not really about 3i Atlas or AWS or space weather. The question is about us, about what this moment reveals when we hold up a mirror and look honestly at what we've built, how we observe and how vulnerable we actually are. In October of 2025, an international summit on space governance convened in Geneva. It was attended by representatives from space agencies, tech companies, defense ministries, and academic institutions. The agenda covered autonomous space assets, digital sovereignty, orbital debris management, and space defense policy. One session focused specifically on the intersection of cyber infrastructure and space-based systems, acknowledging that the two domains are no longer separate. Our communication networks depend on satellites. Our observation capabilities depend on cloud computing. Our ability to respond to threats, whether terrestrial or cosmic, depends on infrastructure that is increasingly centralized, interconnected, and fragile. The summit didn't produce binding agreements, it rarely does. But it did surface uncomfortable truths that have been circulating in policy circles for years. We have created systems of extraordinary capability and extraordinary brittleness. A single cloud provider hosts critical infrastructure for governments, corporations, research, institutions, and individuals. A single point of failure in that system can cascade across continents, disrupting services that billions of people depend on. And we've done this not through careful planning, but through gradual accretion. Each organization making rational decisions that collectively create irrational risk. If we worry about alien probes, about interstellar objects that might carry unknown intentions or capabilities, maybe we should direct some of that worry inward. Because the most immediate threat to our observational capacity, our communication networks, our scientific infrastructure doesn't come from space. It comes from the fact that we've concentrated critical functions in systems we don't fully control, operated by entities whose priorities are commercial rather than civilizational. When AWS goes down, it's not because Amazon wants to disrupt the world. It's because the complexity of managing infrastructure at that scale inevitably produces failures, and the economic incentives to build redundancy have limits. The hidden window concept applies equally to our digital world and to the cosmos. When 3i Atlas passes behind the sun, we lose direct observation. We're blind temporarily to whatever the object is doing. That bothers us because we value visibility, the ability to track and monitor. And no, but we accept far larger blind spots in our own infrastructure without much concern. How many people understand how cloud computing actually works? How data moves through networks where it gets stored? Who has access? How many organizations have audited their dependencies, mapped their vulnerabilities, tested their resilience to cascading failures? The digital world is full of conjunctions, moments when critical systems become invisible or unreachable. And we navigate those moments on faith that someone somewhere is paying attention. This isn't an argument for paranoia, it's an argument for honesty. The same curiosity that drives us to study interstellar objects, to build gravitational wave detectors, to map black hole echoes should drive us to examine our own systems with equal rigor. We should ask hard questions about cloud dependency, about the concentration of infrastructure control, about how transparent our observational systems actually are. Because if we can't see our own vulnerabilities, if we're not willing to acknowledge the blind spots in how we've organized our technology and society, then we're not really prepared for disruptions, whether they come from cosmic coincidence, human failure, or deliberate attack. The outage on October 20th revealed something important. It showed that services millions of people rely on can vanish in minutes, not because of exotic threats, but because of mundane technical failures. It showed that our infrastructure has single points of catastrophic failure, and that those failures can align with other events in ways that create doubt, speculation, and information vacuums. It showed that we're not as resilient as we like to believe, and that our response to disruption is often reactive rather than prepared. 3i Atlas will re-emerge from behind the sun. Astronomers will resume observations, tracking its trajectory, analyzing its composition, debating its origin. AWS services will recover. Engineers will publish post-mortems. Systems will be patched and improved. Life will continue. But what we missed during that conjunction, during that outage during the window, when multiple systems became unreliable at once, might matter more than we realize. Because disruptions don't always announce themselves. Sometimes they're subtle, gradual, encoded in delayed signals that we won't recognize until years later, when someone goes back through archived data with new tools and new questions. The narrative we've constructed around this event, the speculation about cosmic anomalies and infrastructure attacks, is less important than the underlying reality it points toward. We live in a moment of extraordinary capability and extraordinary fragility. We can detect gravitational waves from colliding black holes billions of light years away, but we can't keep a cloud provider running without occasional catastrophic failures. We can spot interstellar objects entering our solar system, but we lose track of them for weeks when they pass behind the sun. We talk about defending Earth from cosmic threats while ignoring the fact that our most critical infrastructure is controlled by a handful of private companies operating on quarterly earnings cycles. This isn't about conspiracy. It's about complexity and consequence. It's about recognizing that the systems we depend on are less stable than we assume, and that the gaps in our observation, both cosmic and terrestrial, are larger than we'd like to admit. The October 20th outage wasn't an alien attack. It almost certainly wasn't connected to 3i Atlas except through coincidence, but it was a warning. A reminder that when we build interconnected systems, we also build interconnected vulnerabilities, and that those vulnerabilities become opportunities for failure, whether random or deliberate. So what do we do with this? We stay curious. We ask critical questions. We demand transparency from the institutions that control critical infrastructure. We invest in redundancy and diversity of systems and resilience rather than just efficiency. We acknowledge that being prepared means accepting that disruptions will happen, and that our job is not to prevent every failure, but to ensure we can respond effectively when they occur. We recognize that cosmic humility, the willingness to admit how much we don't know about the universe, should extend to humility about our own creations. 3i Atlas is still out there hidden for now, carrying whatever secrets interstellar objects carry. The servers are humming again, packets flowing, apps responding. The sun continues its 11-year cycle, occasionally hurling plasma into space. AI algorithms sift through archives, finding patterns we missed. Black hole echoes carry information from decades past. All of it continues overlapping, intersecting, creating moments of alignment that feel meaningful because we're wired to see patterns, to construct narratives, to make sense of randomness. But sometimes the pattern is real. Sometimes the alignment matters. And the fact that we can't yet tell the difference, that we're still learning to read the echoes and interpret the gaps, means we should stay vigilant. Not paranoid, not frozen by fear of invisible threats, but awake to the possibility that what we didn't see during that window, what got lost in the blind spot behind the sun, and the chaos of a global outage, might be the most important part of the story. The next revelation may not come in light. It might come in shadow, in the analysis of delayed data and machine learning algorithms finding correlations years after the fact. It might come when we least expect it, when we've moved on to other concerns and forgotten about that strange week in October 2025, when everything seemed to happen at once. Or it might never come at all. We might never know what we missed, but we'll keep watching. We'll keep building. We'll keep trying to see clearly while acknowledging that clarity is always partial, always provisional, always subject to revision when new information arrives. That's the condition we live in, caught between what we can observe and what remains hidden between the systems we control and the ones that control us. The mirror turns on us, and we see ourselves reflected in the same darkness we project onto the cosmos, fragile, curious, reaching toward understanding, while standing on infrastructure we barely comprehend. Stay awake, stay critical. The universe isn't finished revealing itself, neither are we.